Okay, this is Physical Science 103. And what I'm going to try to do with this video is to make sense of the PhET simulation called Wave on a String. So what you want to do is, let me share the screen first and show you what you need. Let's see, this one right here. So you're going to need this document, PhET Simulator Wave on a String. And we're going to skip the first part, these definitions. You just have to look those up and write in the definitions for each one of these. And don't just write them in and forget them. Write them in and know what they mean, because you're going to be using this information to answer questions and do calculations in the rest of this document. All right, so there are, I believe, 2 experiments that come with this simulation, if I'm not mistaken. Yes. Okay. So once you have your document out, and this is where we're going to start with the speed of the wave and tension. So I'm going to stop this share, and then I'm going to call up the simulation, and we're going to run from the simulation. And if I need to do anything on the board, it's here. If not, I probably will, because there are some calculations. Okay, stop that share. Now I'm going to share the simulation. There it is right there. Okay, for my benefit, I'm gonna stretch this thing up some. Go. All right. So if you look at your document, you'll find that we have to set certain conditions when we start. The first one, the condition is the pulse. So up here in the upper left, we set the pulse. Okay, it opens up another. These things are context sensitive, so when you select something different, you may get access to other variables. So we set it for pulse. We've set it for fixed end, which is here. This is fixed end. You can change it different ways, but for this particular experiment, we want fixed end. We want no damping. So we'll go down here to the slide it over to no damping. And tension we want on low. Slide that over to low. And then, let's see, one other, check normal. Normal's okay in the beginning. We may select slow motion at some point during these simulations, because things happen a lot slower and it's easier to get an idea of what's going on in the simulation. But for now, we'll set it on normal. We want rulers. All right, there we go. So we can measure distances, both amplitude up and down, and longitude left to right. Rulers, timer. We want the timer also. And it says to leave the amplitude and the pulse in the default condition. All right. Now use the ruler to measure the length of the string. This thing with the red and green balls on it is the string. So we want to measure the length. All right, we've got this. Notice that the 0 centimeters is set right on that green dot. So we want to say, how long is it? It looks to be, this is centimeters, so it's 7, 8 centimeters. So each one of these is 2/10, 2/10, 4/10, 7.5 centimeters it appears to be. 7.5 centimeters. That's how long the string is. Okay, and there should be a place to write that. Yes. In the first table on page 3, string length is equal to 7.5 centimeters. All right. So let's see what else we need to do. Click the pulse button to send a pulse down the string. And notice that the wave pulse reflects off the fixed end and undergoes inversion. What inversion means is the wave might be this way, and then on the other side of that fixed point, it'll go back the other way. So let's send a pulse and just see what it says. So you click on this button right here, and that sends the pulse. And there goes our pulse. Right? Right? It inverted. It's going backwards. Okay, and it's just going to keep doing that until we stop it. So if the end were loose, the reflected wave pulse would not invert. I'm not going to take time to do that right now because this video is going to be long enough as it is. Use the timer to measure how long in seconds it takes for the pulse to travel back and forth 5 times. Right? So we start our timer when it hits the back. There. I just started my timer the moment it started. Okay. Down and back 5 times. All right. Just count them off. That's 1. Kind of boring, isn't it? That's 2. We're working on 3 now. Right, that's the end of 3. We're on number 4. And I got my finger poised over the stop button so we can tell exactly when pulse 5 is finished. We're on, that's 4. Now we're on 5. Ready? Bam. Okay. 59.78 seconds. I think I would round it off to 60 because there's some variability in when I see the pulse reach the end and when I click the button. So I think it would be safe to call it 60. 60 seconds to go 5 lengths. Okay, and you put that in your time to travel in the table. Let's see, what's next? Click the restart button. There it is right there, restart. It saves, it doesn't change anything else. It's just restarted. Change the tension to medium now. Change the tension to medium. Tension, here we go, medium. All right, now we need to reset our timer. We're going to go, repeat. We're going to go 5 steps again. Okay. So be sure and record these things in your table. 60 seconds for low. Now medium. We need to reset our clock. So we hit this curve button right here. All right. Ready? All right. It's kind of hard to do both at the same time. So I think what I'll do is send it down once and hit it when it comes back. And that'll be the start. Ready, go. That's 1. That's 2. That's 3. That's 4. And that's 5. 20 seconds. All right, 20 seconds on medium. Put that in your table under time to travel for medium. 20 seconds. All right. Now, I bet the next one's going to be on high tension. Okay, so now let's restart. Okay, set our tension on high. And we're going to send a pulse, and this is going to move pretty fast. So be ready with your timer. Going to go down and back once. Damn. Oops. I forgot to reset it. Okay, let's do it again. Damn. There we go. It's 1, 2, 3, 4, 5. 12 seconds. Let's try that again. There. I want to catch it on the upswing. That's it, 12 seconds. Okay, so you put those in your tape. We can stop that now. All right. And then the calculations that you've got to do, actually, doesn't look like it gives you a lot of instructions on how to do the calculations. How does tension affect, this is number 10 on page 3. How does tension affect the speed of the wave in the string? Okay. These calculations are really very simple. You know how long it takes to make 5 trips. So what's the time to travel 1 round trip? Just divide the values by 5, right? So 60 divided by 5 is 15. 20 divided by 5 is 4. And 12 divided by 5, can I do that one in my head? 2 1/4. 2.2 maybe. Let's say 12 divided by 5. Now 2.4. Now, what's the length of 1 round trip? Well, we measured the string, right? Right. So if it goes down once and comes back, it's double, correct? Now, here's the real catch. Here's the real, this is the pot of gold at the end of the rainbow. What's the speed of the wave? The length it takes, the length it travels in how many seconds? It travels 7.5 times 2 is 15 centimeters in 15 seconds. Right? So the speed of the wave, we're going to call it V. 15 centimeters in 15 seconds equals 1 centimeter per second. Okay? And do that for the rest of them. Now, you can answer question 10. How does tension affect the speed of the wave in the string? You do those calculations and you'll see how the tension affects the speed of the wave. All right. That was the easiest one just to get warmed up. Now we want to set conditions, change the conditions. Change the conditions to oscillate. Leave the fixed end. Damping equals none. Okay, we're still damping none. Tension equals medium. So we're going back to medium. There we go. Amplitude. Now we're going to set the amplitude. The amplitude on the wave is going to be 0.5. So you can either run the slider if you're really good with handling these things. You should be able to go in. No, we go. There we go. You can use the arrows to click. 0.5 centimeters. And the frequency is 0.5 hertz. So you did your definitions on the first page, so you know what a hertz is. All right, just run it all the way down. It looks like it's going to be the smallest one. Oops, too far. Almost the smallest one. Okay, check normal, normal, normal. Where's normal? Normal, okay. Rulers and timer. All right, I'm gonna reset my timer. Okay. So use the ruler to measure the length of the string to centimeters. In centimeters should be the same as experiment 1, right? We did that before, 7.5 centimeters. And if you look at your table, there's a place for that also, just like the previous table. There's a place for the tension, there's a place for the amplitude. Just write those in. All right. Okay. Record the tension, amplitude, calculate and record the speed, in this case, velocity, of the wave in the table. It should be the same as in experiment 1. Assume wave velocity is constant throughout the experiment. Okay. So the speed of the wave, now this is a different calculation, right? Actually, it's one of the calculations that you did earlier. This is medium. So we know the speed of the wave because we can calculate it. The length of the string divided by the time it takes, right? Now, I'm not going to tell you that value because that'd be defeating the whole purpose. But there's a value in the first table for the speed of the wave. That's what goes here. And the speed of the wave is constant. The speed of the wave follows this formula. It's wavelength. Let me see, what are they using for wavelength? Lambda, okay. Wavelength times frequency. Okay, and in your definitions that you looked up, the wavelength, in this case, is going to be centimeters. Right? Times the frequency. What's the frequency? Right? It's how long it takes a wave to pass a fixed point. Right? It's usually written as hertz. Right? But hertz is another way of saying cycles per second. See, I'm just giving you these definitions. Cycles per second. The cycle is a dimensionless number. It has no value. It just means a one wave passing a point. So in this case, the real measure here is seconds to the -1 because it's in the denominator. Seconds to the -1. So when you multiply this times that, you get centimeters per second. So velocity is always wavelength times frequency. But you need to know these units. Frequency is almost always in terms of seconds. Wavelength can be different. It can be meters, it can be seconds, it can be nanometers. The sky is the limit. But in our case, it's centimeters. Centimeters per second is velocity. So what you need to know is how long is a wave? And in our case, the wave is 15 centimeters. And how long does it take? Well, you look at your table, 15 centimeters in, let's see, 4 seconds. Right? So 4 divided into centimeters. This is like saying 1/4 seconds here. All right, and this would be 15. So 15 times 1/4 seconds, 15 centimeters, is 4 into 15. And that gives you your your wave velocity, and that is constant. This is a constant for our particular string under that tension. If you have a different string under different tension, then that value will be different, right? That's how guitars work, right? You have a heavier string under different tension, gives you a different note, and that note is what we interpret as frequency or speed of the wave, whichever the case may be. Okay, so now we got those values in our table, and the speed of the wave is the same for every harmonic. Now, what's a harmonic? If any of you in this class are musicians, then you either know what a harmonic is or you use harmonics when you play your instrument. You may not know what a harmonic is, but you are definitely using one, particularly if you're using a wind instrument. If you're using a wind instrument, then you finger up a certain distance, and then you got to go back and start again, or maybe with different fingerings, depend on the instrument. What you're doing is you're accessing different harmonics of that particular length of woodwind. For saxophones, you run the scale, and then you start it all over again, only with a higher range. You're accessing different harmonics. And those of you who've been at it for a while are able to go way up there. They call that the Altissimo range. I never was very good at that. I got one note on the Altissimo off of my saxophone, but I never got better than that. But there's some who can go 4 octaves. I was only able to go just beyond 2, maybe more than that. Yeah, because the normal range on the instrument is let's see, from low B flat up to high F. Right, so it's probably about 3 octaves normal. So you go up to 4 or 5 octaves if you're good at it. But that's neither here nor there. The point is, if you play any musical instrument, you're accessing harmonics. Now, a vibrating string will actually be vibrating with several different frequencies at the same time. If you play a guitar, you know that if you pluck the string and you just touch the string, just the right place and the right pressure, you can access a higher harmonic on that string. Okay, so what do we mean by harmonics? Well, there's the fundamental, which is the first harmonic. This is the absolute longest possible wavelength you can get out of the string. And what do we mean by that? Well, we know that waves travel like this. Right? So what's a wavelength? Well, the best way to tell a wavelength is from the baseline. So we start here, and we want to go, well, actually, you can do it several ways. You go from the baseline, up, across the baseline, and back. So when you start to go up the baseline like you are here, again, that's one wavelength. Or sometimes we say go from crest to crest. Right? That's one wavelength. The first harmonic is the longest wavelength possible on that string. And the longest wavelength possible is between the two ends. When the two ends are like here, we had our fixed end here and our moving end here. That's only a half of a wavelength. So the wavelength is, for a 7.5 centimeter string, is 15 centimeters. That's the fundamental. That's first harmonic. Okay. We tell harmonics by the nodes and the antinodes. So with this string, the number of nodes it has, a node is where the string is not vibrating. Right? It's on the baseline. So this string has one antinode and two nodes. So if you look at your table, you see the fundamental, you look over to the right, number of nodes, 1, 2. Number of antinodes, 1. For the string, right? This varies from, if we were talking about compression waves in a wind instrument, we'd be talking a little bit differently. But the fundamental has a wavelength of 15 centimeters. We said that before. So what's the frequency? Well, the frequency is how long does it take? Right? If we go back to our formula, well, the frequency here, we want the frequency to be our unknown. We know that this is the velocity, centimeters per second, and our wavelength is the length of double the string, so it's 15 centimeters. There's our unknown. Solve for your unknown. So you take 375 and divide by 15, and that's the frequency. So many hertz. All right, it's going to be less than 1. It's going to be a fraction of 1. And that's how you fill in that first row. For the second harmonic, well, let's see. Let's run the simulator for, I've talked enough. Let's run the simulator so you can get an idea of what's going to happen. Let's see. Okay, there's the formula. Step 5, there's your velocity equals lambda times frequency. Okay. It defines what a node and an antinode are. Between 2 nodes. All right, it's not telling us to start the sim at all. Hold on a second. Calculate and record the speed of the wave in the table. Use the ruler. Okay. We're supposed to be generating a standing wave. Okay, let's just start it. Let's see. Okay, here's our start button. So let's see what happens. All right. Every once in a while, you'll see the center of that wave, that green ball, fixed. And you'll see the waves oscillating this way. That is the second harmonic. Why do I know that? Because that length, 7.5 centimeters, is covers a full wavelength. You've got an up and a down fixed at the ends, and that's a full wavelength, 7.5 centimeters. So if we go to our table, we find that the wavelength for the second harmonic is 7.5 centimeters instead of 15. Okay, I hope you see that. This is what's called a standing wave. And that's where harmonics come in. You only see harmonics when you can generate a standing wave. Now, it's a little It's not perfect because one end is not perfectly fixed. It's moving. It has to move in order to add energy. All right, so if you let it go, it's just going to go wonky forever. So let's restart it. And let's hold on a second. Pause. Let's slow it down. Now we can see things happening. Here's a proposition. If you have that pulse that we had in experiment 1, and you send the pulse down the line, and it's going to go down if the string is long enough and bounce back. Well, if you make the length of the string short enough, then the pulse is just going to have time to go up once, bounce, and come back down. That's a standing wave. And you have many standing waves that can happen within that length. The first harmonic is the longest standing wave. The second harmonic is the next shortest wave, and its wavelength is equal to half of the first standing wave. The third harmonic is a fraction of the fundamental. Always go back to the fundamental. So the second harmonic of the fundamental is half. The third harmonic is a third. The fourth harmonic is a fourth of the standing wavelength, the first harmonic. And the fifth harmonic is a fifth of the wavelength of the first harmonic. Right? So that's fairly easy to calculate. You just use the second, third, fourth, fifth as denominators of your fraction. And notice while we're going here, let me start it over again. Restart. There we go. Okay, once it gets going, now look at how many nodes and antinodes you have with your standing wave. A standing wave looks like it's just standing still. So if it were going fast enough, it's going slow now so we can see it happening. But in reality, the wave, it reinforces itself. And you notice that the longer we let it go, the larger the amplitude. So we're putting energy into this standing wave, and we keep putting energy into it, and it makes it bigger. So, okay, notice how many nodes we have. We got one on this end, we got one in the middle, and one on that end. All right, so that's 3 nodes in the second harmonic. How many antinodes? How many humps do you have? 1, 2. So that's antinodes. How about the third? What if we did a third? Well, in order to do that, we would need to, let's see, we would need to change the frequency, I believe. Yeah, change the frequency. Okay, the frequency should be that one. So let's start it over again. Let's see if it works. And this is where you get to play around. Find out where you have a standing wave. It looks like we got 3 humps forming here. Yep. Notice we got a node here, a node here, a node here, and a node here. So that's 4 nodes. This is the third harmonic. 4 nodes and 3 antinodes. Notice that the number of antinodes is equal to the number of the harmonic. Right? So we calculated the frequency for the first one at 0.25. And the second one at something. I guess it was 0.5. Yeah, we set it on 0.5. And multiples of that frequency, 0.25, 0.5, 0.75, 1, and 1.25, would give you your frequencies. And you can calculate those here. And then you can set them here on the device to prove that you have what you think you have. All right, so let's restart. And let's go up to 4 times, let's see, 50, let's go up to 1. There we go. Now let's restart it and see if it works. We should have a standing wave there with 5 nodes and 4 antinodes. Okay, how many nodes? 1. Got to wait for it to settle down. Okay, it looks like we got a node, an antinode here. 1, 2, 3, 4. 4 antinodes, and 1, 2, 3, 4, 5 nodes. So it worked. All right, so once you get your table filled out, you got to answer some questions. Why can we use the equation V equals lambda frequency without changing wavelength to meters? Well, as long as you're doing the experiment in 1 unit of measure, it's the same unit of measure for each calculation. We could call it meters if you want, but once you get the wavelength set in a certain unit of measure, don't change it, because if you change it, then our calculations fall apart. It's based upon this relationship here, here, and here, right? If the velocity is in centimeters per second, you want the wavelength to be in centimeters and the frequency to be in hertz. If this is meters per second, then you want that to be in meters, and this would be in hertz. All right, so I'm not going to do the others for you. Let's just, we'll just stop it there for a second. So, did the results of the experiment 2 confirm that wave velocity was constant for these conditions? Right? You have to say, all right, is the velocity constant? Well, you did measurements here. It's kind of like working backwards. You did these measurements and you found out that the wavelengths changed and the frequency changed, and they changed opposite to one another. But when you multiply them together, you always get the same number. All right. If I haven't said this before, whenever you've got an equation, say an equation in 2 unknowns, doesn't matter what they are, say A times B equals a constant. If you have a variable A and a variable B, that means they can change. But this is constant. Once this constant is set, if A goes up, B has to go down. That's the only way that you can manage a constant. This is called an inverse relationship. Okay? As opposed to a direct relationship. So when you have a direct relationship, something equal to a constant is A divided by B. Right? So if this is constant, if A goes up, B has to go up in order to keep that constant. That's a direct relationship. Right? You may notice that along the way. Now, the direct relationship doesn't apply to this particular exercise, but the inverse relationship does. Okay. Is there a trend in the frequencies from one harmonic to the next higher one? trend in the frequencies. Frequencies. All right, so you'll have to look at your frequencies and say, first harmonic, fundamental. Second harmonic is a frequency. Third harmonic, how do they vary? Ask yourself this. Can you calculate the second harmonic using only the first harmonic value of frequency? Can you calculate the third harmonic using the first harmonic? And so forth. Ask yourself that question, and I think the answer should be obvious. Okay, that's it. That's all I've got for you. I've given you too much already. You should be able to ace this one.